The research paper introduces a novel approach, Temporal-controlled Frame Swap, TeFS, to generate synthetic stereo driving data for visual simultaneous localization and mapping, vSLAM, tasks. This method overcomes the lack of native stereo vision support in commercial driving simulators, particularly in Grand Theft Auto 5, GTA 5. The authors demonstrate the effectiveness of TeFS by creating the first large-scale GTAV-based stereo driving dataset, GTAV-TeFS, containing over 88,000 high-resolution stereo RGB image pairs along with various ground truth data. This dataset offers several advantages over existing synthetic stereo datasets, including closer to realism environmental complexity, scenarios in both city and off-road environments, and comparison groups featuring controlled road segments under various challenging cases. The quality of the stereo data collected using TeFS is validated through a comparative analysis with conventional dual-viewport data, revealing the distinct advantages and limitations of each method. The goal of this work is to bring more high-fidelity stereo data from commercial-grade game simulators into the research domain and push the boundary of vSLAM models. The authors also introduce a novel method, Temporal-controlled Frame Swap, TeFS, to collect stereo driving data from commercial video games with single viewport limitations. They create the first large-scale stereo driving dataset, GTAV-TeFS, based on the high-fidelity video game, GTA 5, which includes stereo RGB image pairs, temporal information, GPS coordinates, camera poses, and full-resolution dense depth maps. This dataset facilitates up-to-scale stereo odometry tasks in a realistic commercial game environment. The authors highlight the limitations of existing synthetic datasets created from GTA 5, such as the lack of stereo image pairs, which impedes their use in vSLAM tasks. They also discuss the limitations of open-source simulators, including Microsoft's AirSim and Carla, which, although providing comprehensive data collection APIs, lack the level of realism provided by commercial-grade video games due to budget gaps. The authors then provide a comprehensive overview of the implementation of their TeFS method in GTA 5. They describe the interaction with the game environment, the stereo camera setup, the TeFS workflow, the process of obtaining depth maps, and the limitations of their approach. Specifically, they use the script hook V plugin to interact with GTA 5 and attach a pair of parallel cameras to the front hood of the Ego vehicle, Blista, with a stereo baseline of 0.54 meters. The authors propose the TeFS algorithm to address the limitation of capturing stereo data in motion from GTA 5. They introduce several important parameters and internal functions, including the cycle tick parameter to track in-game status changes during the stereo collection process. The TeFS method adopts a single-thread architecture that provides precise temporal control during the camera swapping process, ensuring that the captured image pairs are suitable for stereo odometry algorithms. The Temporal-controlled Frame Swap (TeFS) algorithm is introduced as a novel approach for capturing synthetic stereo data from GTA 5. This single-thread architecture precisely controls the passage of time during camera swapping, leveraging the on-tick function and timescale parameter to avoid temporal disparity. The process involves collecting one stereo image pair every 10 uni-ticks, with the Ego vehicle driving normally for 7 uni-ticks before a pseudopause, followed by a camera swap function execution while the scene remains relatively still. The captured stereo data is evaluated using absolute pose error, APE, and relative pose error, RPE, metrics. The TeFS method is validated using the Carla simulator, demonstrating its universal applicability across various engines and games. Furthermore, the temporally enhanced feature synthesis (TeFS) technique is developed to generate synthetic stereo data from monocular video feeds, enhancing vSLAM model accuracy and reliability in diverse environments and weather conditions. Experiments on Carla and GTA 5 datasets show that TeFS yields stereo data comparable to native stereo API data. A comprehensive evaluation of 3 feature-based vSLAM models, including ORBSLAM3, VINS Fusion, and OV2SLAM, is conducted on the GTAV-TeFS dataset under different weather conditions. The results indicate that ORBSLAM3 demonstrates superior robustness and accuracy in the extra sunny condition, while maintaining its dominant edge across all road segments in the rainy scenario. However, under the night with thunderstorm scenario, all models suffer performance degradation, with OV2SLAM being the only model to generate complete results. The evaluation concludes that ORBSLAM3 provides reliable performance and exceptional loop merging capability under normal and moderately noisy environments, while OV2SLAM demonstrates remarkable robustness in hazardous situations. The Temporal-controlled Frame Swap (TeFS) method is introduced as a novel approach to overcome the single viewport limitation in commercial video games, enabling the dynamic collection of high-quality stereo driving data. The GTAV-TeFS dataset is created, providing a valuable resource for evaluating and enhancing stereo vSLAM algorithms. The effectiveness and generalizability of the TeFS method, as well as the quality of the collected stereo data, are scientifically analyzed and confirmed. An evaluation of various feature-based and learning-based vSLAM models on the GTAV-TeFS dataset is presented, with the DROID-SLAM model demonstrating great accuracy in sunny weather conditions and outperforming other models in rainy and thunderstorm scenarios. However, it has drawbacks such as long evaluation time and high hardware requirements. Visual comparisons showcase the actual differences among the resulting outputs of the TeFS, native stereo, and the simple swap method, with the TeFS method producing minimal temporal offset, making it suitable for depth-related tasks. The paper highlights the potential of the TeFS method to aid in the development of future surrounding view data acquisition tools, expanding data collection capabilities and presenting exciting avenues for the advancement of future autonomy models. The research emphasizes the importance of accurate and detailed synthetic data for training and testing AI models, highlighting the limitations of current datasets and proposing new methods for generating more realistic and diverse synthetic images. The authors discuss the cost and complexity of creating such datasets, citing examples from game development and simulation, and demonstrate a deep understanding of the technical challenges and potential benefits of advanced stereo synthesis techniques.